Yeah, so then
No, és que no m'agrada.
No t'agrada el meu maig. No t'agrada el meu.
no. Okay, so we're pleased to have the last talk of the morning session and actually of the day. David, Martí-Pete from Liverpool.
Okay, thank you very much. Thank you for the invitation. It's always a pleasure to return to Warsaw, and yeah, I had not been in Warsaw, I think, since I left as a postdoc, so it's very nice to be back. So you might have seen me talking about similar thoughts, but okay, so this is about constructing counterexamples to Eremenko's conjecture, and when we were working on this topic, the initial motivation was to construct wandering domains. So usually when I speak about this topic, I talk more from the point of view of wandering domains in terms of what is the geometry, what sets can be wandering domains. But for today, I thought that I would give a talk that is only focused on Eremenko's conjecture, so I will try my best not to mention wandering domains. If you want to hear the talk about wandering domains, then you need to come to Henshin next week, and I will talk about wandering domains there. Okay, so this work happened around between 2020 and 2021. This is a joint work with Rempe and James Waterman. At that time, we were both postdocs with Lasse in Liverpool. And here you have the reference of the paper on the archive. So I think most of the things that I will introduce, Andrew already described, so I can go a little bit faster. So the topic of this talk is the escaping set of a transcendental entire function. So for entire functions, the escaping set is just the set of points that when you iterate, then their orbit tends to infinity. This set is very different from a topological point of view, depending on whether the entire function is a polynomial or it's a transcendental entire function. Here in the left, you have a picture of a quadratic polynomial. So for polynomials, the escaping set is an open neighborhood of infinity. The points that are not in the escaping set for polynomials, they always have bounded orbit, which is this black set here. And it's a bounded set. If you iterate a transcendental entire function, then the situation can be a bit more complicated. It's not always an open set, and it has many interesting, the escaping set has many interesting properties from a topological point of view. And here you have an example in the right. In this example here, the escaping set consists of an uncountable collection of curves to infinity, together with some of the endpoints of these curves. The points in the black set here, again, they are basin of attraction, I believe. But one other difference between the iteration of polynomials and that of transcendental entire functions is that besides having these two behaviors of escaping to infinity or having bounded orbit, for transcendental entire functions, we need to keep in mind that we can have this third behavior of having unbounded orbits that are non-escaping, right? So this would be, in this example here, some other of the endpoints of these curves. So the situation is very different. For this talk, I will talk about transcendental entire functions, so it's good to have the picture on the right in mind. Okay, so as we mentioned before, the first person to study the iteration of transcendental entire functions was Fatou. And in this paper from 1926, he studied two concrete families of examples. There are these two functions here. And he proved that they contain, so this one here is this function on the right. And he showed that for this function, there are some curves that go to infinity. So for example, you can look at the restriction of the function to the imaginary axis, and you can see that there is this half line here and this half line here, that when you iterate, these sets are invariant and points go to infinity. So this was already discovered by Fatou, as I said in the first paper in Transcendental Dynamics. And then later on, it was discovered that many functions have these properties, right? There is a whole collection of papers by Devane and some co-authors. I just put one here as an example, where they look at functions for which the escaping set again consists of this, what they call Cantor bouquet of curves. So uncountable collections of curves where points along these curves tend to infinity uniformly, right? So around the same time of the Devane papers, there was also this paper from Eremenko where he looked at the escaping set of transcendental entire functions in complete generality. So he proved these three things here. He proved that the escaping set is never empty, right? So there are points. He did this by constructing what now we call Eremenko points, which are points that escape to infinity really fast. He also showed that the Julia set is the boundary of the escaping set. So just to compare, okay, so this first property, the escaping set always means the Julia set. If we go back, for polynomials, this is the opposite, right? For polynomials, the escaping set is this red set here. So this is the basin of attraction of infinity, is completely contained in the Fatou set. But for transcendental functions, there are points in the Julia set always that are in the escaping set. This other property here, that the Julia set is the boundary of the escaping set, actually, if we compare, this is true in both cases, in the polynomial side and in the transcendental side. Right, like the boundary of the Julia set in the polynomial case, the boundary of the filled-in Julia set is the boundary of the escaping set. And this is true also in the transcendental case. And then the third property that he proved is that when you look at the closure of the escaping set, then all the connected components of this set are unbounded. Okay. So the conjecture that he made in this paper in 1989 is that the same was true actually if you remove the closure, right? So this is the theorem, and just before the theorem he said it is plausible that the escaping set has no bounded connected components, and we shall prove this weaker statement. And this has remained an open question for a very long time and has motivated a lot of the research that has been going on in transcendental dynamics and produced a lot of very nice results. In the same paper, he also made a stronger conjecture. The last sentence actually of the paper says, it is plausible that the escaping set always has the following property, that we can join every point of the escaping set to infinity by a curve in the escaping set, in the same type of behavior that Fatou had observed or that Devane proved with several co-authors. Okay, so we have these two conjectures. Now, there is another property that is related to these two conjectures. So here are the statements of the two conjectures done by Eremenko. Phil Rippon and Gwyneth Staller proved that, in fact, we always have that when you add infinity to the escaping set, this is always a connected set. And in a sense, these three things look somewhat similar. So if you're not used to think about this, you may think that they are, so why this does not solve the other two? And the thing you should have in mind is something like that. If we have infinity here, we can have some collection of unbounded curves, right? Such that their accumulation set they accumulate at some other bounded component of the escaping set. So these bounded components are not somehow isolated. If they happen, we knew for a long time that they would need to be accumulated by other unbounded components of the escaping set. So if you wanted to separate this, you would need to go through infinity. If you want to separate this set, you really need to use infinity. So the escaping set union infinity is a connected set. Okay. So the history about Eremenko's conjecture is quite interesting. So a lot of progress has been done by looking at this nicer set, which is called the fast escaping set. Okay, the fast escaping set is a subset of the escaping set that was introduced by Bergweiler and Kincannon in 1999, and consists, roughly speaking, of the points that escape as fast as they can. So I can draw here, maybe here, maybe there. One sec. So the fast escaping set, you should think about it like this. We take a disk of radius r, then we look at the maximum value on this disk. There may be several points where this maximum modulus happens, and then we draw the disk of radius m of r, and then we do the same. We look at this large disk, compute the maximum modulus. This gives us a new radius, and we call this m2 of r. So we keep iterating this, and then we say that the point is fast escaping if maybe for a certain number of times the point jumps around a little bit, but there is some point that it starts beating the maximum modulus at every step. So in terms of this partition that I've drawn using the maximum modulus, a point is fast escaping if after some point every time jumps one of these circles. Okay. So one of the reasons why this set is nicer is that it has this property that we want. So the connected components of the fast escaping set are always unbounded. So they are much nicer to study than the escaping set itself. And then in particular, this means because all these components of the fast escaping set, they are contained in some component of the escaping set. So in the worst case that they were all in the same component of the escaping set, you could at least have one unbounded connected component. We don't know, I believe, if every component of the escaping set meets the fast escaping set. No, actually it does not, because otherwise Eremenko's conjecture would be true. Okay, so we know that there is at least one component of the escaping set that is unbounded due to this fact that the fast escaping set has all the components unbounded. So using this direction, there has been a lot of progress on Eremenko's conjecture. So there are several classes of functions for which we know that the escaping set is connected. Hence, if it's connected and at least one component is unbounded, then every component is unbounded in this way. So Phil and Gwyneth use this approach of using this structure that they call spider's web to deduce that the escaping set of many classes of functions is connected, and hence they satisfy Eremenko's conjecture in this easy way that there is just one component, and this component is necessarily unbounded. Okay, and the strategy to prove this is that they always show that a subset of the escaping set is what they call a spider's web. So you should imagine some set that looks like this. Right. So they prove that if a subset of the escaping set is a spider's web, then the escaping set itself is a spider's web, and in particular, it is connected, right? So this is how this works. To show that the first escaping set is a spider web, then the escaping set is connected. There are also functions for which this does not go like this, that the first escaping set is not a spider web, but still the escaping set is connected. This was proved by Basso. So this function here, which happens to be the other function that Fatou studied in the paper. So for this function, the first escaping set consists of the collection of black curves together with some of the endpoints again. The gray set here is a Baker domain. So points that are black in the curves here, they escape fast to the left. Points in the gray set, they also escape, but slowly by moving roughly like translation by 1 to the right. The complement of these two behaviors are some of the endpoints of these curves, which need to do everything else that needs to be done. So in the endpoints, there are oscillating points, there are points that escape, but not fast escaping, etc. Okay, so Basso proved that for this function, the escaping set is again a connected set, so this function also satisfies Eremenko's conjecture. Okay, so I split the talk into two parts. The first part is actually about talking a bit about counterexamples to the strong Eremenko conjecture. And the second part is about talking about counterexamples about Eremenko's conjecture itself. Of course, every counterexample to Eremenko's conjecture is a counterexample to the strong Eremenko conjecture. But this part here is an easier construction. So I think it's worth to look first at the strong Eremenko conjecture and then move on to the next one. As a reminder, so the strong Eremenko conjecture says that every point in the escaping set can be connected to infinity by a curve of points that escape to infinity. Okay. So in other words, like the escaping set union infinity is path connected. So again, as Andrew explained before, the first counterexample to the strong Eremenko conjecture dates back from 2011. It was given by Rodenfuser, Rucker, Rempe, and Slacker. So their counterexample. So first of all, okay, so they gave two results. So one is a positive result, and the other one is a counterexample. The positive result says if you have two conditions. So one is the function is in class B, and the second condition is that this function has finite order, and you can also relax this to have finite compositions of functions of finite order. Okay, so with these two conditions, then the strong Eremenko conjecture holds. So we can connect points within the escaping set, we can connect points to infinity by curves. Okay, so so this condition of finite order, actually, in the paper, this is translated into some geometric conditions on the tract of the function. So Andrew talked about these logarithmic tracks. So let me just draw a picture maybe. So if you have your set of singular values, right, and you consider a disk, then you look at the preimages of these disks. These are some tracks. Right. So the geometry of these tracks tells you that so if these tracks have sufficiently nice geometry, then the strong Eremenko conjecture is true. And in particular, functions of finite order, they satisfy these nice geometry conditions to ensure this. On the other hand, they also gave this counterexample that Andrew was talking about. So their counterexample is a function in the class P, and they prove in the original theorem that the components of the Julia set, they are all bounded. Now, for functions in the class B, it follows from a result of Eremenko and Lewis that the escaping set is a subset of the Julia set. So in particular, the path connected components, I should say. So in particular, the path connected components of the escaping set for this function, they are also bounded. And Andrew is looking at actually more than knowing that they are bounded, what type of topology this set has, right? Okay. So this is this counterexample to the strong Eremenko conjecture. So part of the things that we did in this joint work with Lasse and James is to construct new counterexamples to the strong Eremenko conjecture. So first, let's recall that a continuum is a non-empty, compact, connected metric space. And we say that it is full if it has no bounded complementary components. Okay? So a version of our result is if you have a path connected full continuum, maybe to have in mind, one second. So I think you could have in mind something like what is habit. Might be helpful. You can think that this is the set K, right? Path connected full continuum. Then there exists, we show that there is a transcendental entire function for which this exact set is a path connected component of the escaping set. So here I should remark that this is not that this set approximately looks like or is homeomorphic to a component of the escaping set, but here we're talking about the exact same set itself. So you give me a set, and this theorem gives you the function for which the exact same set is a path connected component of the escaping set. Okay, so I should say that this first version of the result, the ideas behind it, most of them are already in the work that very inspiring work that Luca Vogtaler did in 2021, where he looked at how to construct functions with prescribed wandering domains. Okay. So I think he was motivated actually to, his motivation I think was to, for example, construct a transcendental entire function for which a disk can be a wandering domain. But he proved a much more general result. But this is the only mention I wanted to do to wandering domains. So they are really behind the motivation of why we prove some of these things. But today I will just talk about it from the point of view of Eremenko's conjecture. Okay, so again, we have a path connected full continuum K. We want to construct a transcendental entire function. So this sort of problem usually is solved by, so there are several ways how we can construct functions. One of them is approximation theory. And the most classical result in complex approximation theory, I would say, it's Runge's theorem. So Runge's theorem tells you that if you have a compact set with a connected complement, right, and phi is an analytic function on a neighborhood of this compact set, then for every epsilon, you can find a polynomial that approximates f, right? So you prescribe the function phi on this compact set K, and then for every epsilon, you find a function that is entire and it's a polynomial, and it's epsilon close to the function phi that you prescribe for all the points on the compact set. right? This is a very, very classical result of approximation theory. And this is what we will use to construct this function for which K will be a path connected component of the escaping set. Okay, so again, so we will construct a transcendental entire function f with these properties. The set K that we started with will be a subset of the escaping set, and the boundary of the set K will be a subset of the Julia set of the function. This is the task that we want to accomplish. Are there any questions up until here before we enter the proof? No? Okay. Feel free to stop me at any point. So how do we do this? So again, this idea goes back to Bob Thaler, which is the following. So the main idea is you have your compact set K that I put in black here. And what we will do is that the boundary of the set K will be approximated by tiny preimages of a basin of attraction, basically. So in particular, we will get that the boundary of this compact set needs to be in the Julia set because it's accumulated by other photo components. So we start with the set K. The first step is to write K as an intersection of compact sets. Here I put them in dark gray. So any compact set K, for every compact set K, you can find a sequence of full compact sets that satisfy this property that the intersection of this collection of full compact sets equals K. Right, so you keep approximating, getting closer and closer to K. So we will use this sequence of compact sets Kj. And we also need another ingredient, that is, for each of these compact sets, we will choose one point. So we will get a sequence Pj of points by taking a point in each of these gray compact sets, with the property that this sequence of points accumulates at the whole boundary of K. Okay? So the accumulation of this sequence of points that we can choose needs to be the whole boundary of the set K. Again, this follows from some easy topology properties. Okay, so again, we start with K, and now we have two more objects. We have a sequence of full compact sets whose intersection is K, and we have a sequence of points that belong one of them in each of these compact sets, and they accumulate to the full boundary. Okay, so what do we do with these two ingredients? The construction will be an iterative construction. So we will obtain a sequence of polynomials, Fn. Each of them will be reduced by Runge's theorem, right? So we will invoke every time Runge's theorem, and we will get a new polynomial. Now, for this sequence of polynomials to converge, we need to make sure that they are not really different from each other, right? The sequence of polynomials will, if you fix a large compact set, then all sufficiently large polynomials in the sequence will be close to each other. In other words, we will have, if you look at the sequence of larger and larger compact sets, then this sequence of polynomials will be converging on this set. So the function Fn plus 1 will be defined to be really, really close to the function Fn on a very large compact set. And then we will modify it a little bit outside. And then in the next step, we will choose an even larger compact set where Fn plus 2 will be very close, even closer to Fn plus 1. And then we will change it a little bit outside. So this is the idea. Okay, so what properties will these polynomials have? Every polynomial in this sequence of Fn will satisfy that this disk here will be mapped inside itself. Okay, so we pick a disk and we force the function. So one easy way to force the function to map a disk into itself is to define the function to be on this disk to be equal to the center of the disk and have an error epsilon that is smaller than the radius of this disk, right? So it says like this radius is, I think it's -3 or something like that. So if you define the function to be on all these disks, the constant function -3, and your error epsilon is smaller than 1, which is the radius of this disk, then it will satisfy this, it will map inside. Right? Note that once you have this property that the disk mapped inside, there is an attracting fixed point, and the whole disk is contained into the basin of attraction of this point. The second observation is that once you have this property, if you add a small error, this property will not change. You have a disk that maps strictly into itself. If you add a sufficiently small error, the same disk will still map into itself. Right? So all the functions that we will consider, they will all satisfy this. So all this sequence of errors that we will keep adding and adding, at the end of the day, they will add up to an error that is sufficiently small so that this disk maps still inside itself. Right? So all the functions satisfy that this exact disk is contained into a basin of attraction. Okay, so what are the other properties we want? Okay, so you should imagine that this picture here, it's here, in this disk, D0, right? So in D0, we have the compact set K and all these levels, the KJs, right? And all these sequence of points, little PJs. So on the first step, the outer level, so maybe here there is one level missing. So basically imagine that here there is the P1. So we will map P1 into this disk. Again, we can define the function to be equal to the center of the disk. So the first point will move here, and the first level will move one to the right. Okay, what do we achieve by this? So since P1 maps into this disk, and this disk is a basin of attraction, this means that the point P1 is exactly belongs to a preimage of the basin of attraction that contains D-1. Okay, I don't know how big this preimage will be, but I know that the point P1 exactly is in it. If you put an error, then this P1 will not longer be mapped to the center of D-1. But since the whole D-1 is in the basin of attraction, this exact point P1 will still be in a preimage of this basin of attraction. And this, as I said, on the first level, we move to the right. Okay, so this is the function F1. The second level, we take some large disk delta 1, which contains the two things that we have prescribed before, and we ask this function F2 to be very close to F1 so that these properties that I prescribed are still present. And on top of this, we define it on the disk D1. How do we define it here? This point P2 that we had there, we don't know exactly where it has gone, because if you remember, it moved to the right by a translation, but then there was an error. So we don't know exactly where P2 is, but we know where F1 maps it. So this point is now some point here that is F1 of P2. So I can define my function F2 depending on the function F1, depending on what F1 has done. So we also do this in a way that the function from here to here is univalent. So again, if we have translation by 1 and a fine map, and then we have an error that is sufficiently small, then any holomorphic function that is sufficiently close to an affine map will still be univalent. So we can track where F1 maps P2 and where this next level has gone, right? So there is a new black point here, and there is here, this is the image of the next level where it has gone. So we send the new point to D minus 1, and the next level we translate to the right. Okay? So what it happens is that this sequence of points that were accumulating K, their behavior is, or if you have a point pk, I think for k minus 1 times, it has been moving to the right one at a time. And then the last step jumps to d minus 1. Okay? So this means that this sequence pk, they're all in different components of basins of preimages of this basin of attraction. The other sets, they have been moving one to the right at every time, right? So in particular, the set K, which belongs to all these compact sets, the set K has been traveling 1 unit to the right every time. And yes, so it's the only thing that stays moving to the right. Everything outside K eventually peels off to either go to the basin of attraction or do other things. But the set K moves exactly to the right. Okay, so what do we achieve by this? So as I said, we also made these things so that the sequence of polynomials Fn converges. And at the end of the day, we have that K is in the escaping set. And its boundary, because it's accumulated by these preimages of basins of attraction, it's necessarily on the Julius set. Okay? But there is one more thing. I told you that we want to prescribe path-connected components of K be path-connected components. So if K is path-connected, we want to make K a path-connected component of the escaping set. How do we know that these components are not larger? Okay, so at this point, we need to modify a little bit what I told you. So what I told you is that we have this sequence of points that accumulates the boundary of K, right? This is not enough to be able to be sure that K is a path-connected component. So what we will do, we'll draw it a bit larger maybe. Right? This is K. So imagine that this set Kn look a bit like this. Every time closer to the set, okay? So instead of using, so the original version is we pick a point in each of these things, in each of the sets, accumulating the boundary. Now we do a bit the opposite. So we fix 2 points. So suppose that this set, it should be K. This K is not a singleton. So imagine pick 2 points, one here and one here, for example. Okay, and then we make we replace the sequence of points by alternating. So you can draw like a circle around here and a circle around here, and replace this point by things that almost close. So we cannot approximate on things that will close completely, but we leave a gap here around where this point is. Then the next level will leave a gap close to the other one. So we replace P, right, by almost the boundary of the previous level, but with a gap here, and etc. So now we would use, again, something that stops here. Okay, but it goes almost all the way around. So using this, we map exactly the same. So these red sets, we map them to the basin of attraction. Instead of just sending a point, now we map this more complicated set, which is almost all the boundaries of the KMs. So this allows us that to be sure that K will be a path component. So if K is path connected, then K will be a path component of the escaping set, because if there was some other path component that was larger, what would it need to do? It would need to enter this set, then go around to the other one, then go around to the other one, right? So this looks a bit like this example of the sine 1 over x curve, where the set is connected but not path connected. This curve would not be able to increase or change the path connected components of K. So we are sure that the path connected set K is in fact a path connected component of the escaping set, because it could not grow any larger because these sets are preventing it. Any questions about this?
Yeah, sorry. So the
Yes.
points and 1 and 2, these are
So 2 points in your string.
points. You're saying that for any
Any 2 points, yes.
are just defining this PJ
Yes.
around.
It doesn't matter if they are near each other. The important thing is that there are 2 different points. So your curve needs to oscillate between 2 points, 2 places in the plane, right? So it doesn't matter if these 2 things are very small, but still, like, you need to oscillate infinitely many times between things that are a positive distance apart.
But picking 2 specific points already, you show this. You don't need to do it for all of them.
No, you just pick 2 points, yes.
It's arbitrary and then
Yes.
already.
Yes. Okay. Then you can say, okay, what if you don't have 2 points, so K is only 1 point, right? But then this is the more trivial case. One option to do that is to pick a continuum for which a point is a path connected component. And this is one example. So this continuum here, which is appending copies of this continuum satisfies that this point here is a path connected component of this continuum. So if you use this as K, basically this will still be a path component of the escaping set of the resulting function. Yeah. So in a sense,
How do you separate this point from any other?
right?
How do you separate this point from?
So the point is that there is no curve that starts at this point and finishes at another point.
It's not a kinetic component.
It's a path point. It's a disconnect. Yeah. Yes. So far we're talking about path components. Okay. So in fact, what we prove is basically this: that if you have a full continuum, right, then every path component of K is a path component of the escaping set, and every path component of the boundary of K is a path component of the Julia set. Yes. So this is about the strong Eremenko conjecture. Are there any questions before I move to the Eremenko conjecture itself?
So the
Yes.
resulting function is the limit of
Polynomials. So this function f is the limit of the polynomials fn here that were obtained, each of them by applying Runge's theorem to a larger and larger set. Okay. So now for counterexamples to Eremenko's conjecture, how do we construct them? So this is a reminder. Eremenko's conjecture says the components of the escaping set are all unbounded. So our goal is to construct an entire transcendental entire function with a bounded component of the escaping set. Okay, again, we have here a reminder. So our theorem says that if you give me a full continuum, then there is a function, transcendental entire function, for which this is a component of the escaping set. So, for example, the Mandelbrot set, the Naster bucket handle, many other, all pick your favorite full continuum. There is an entire function. Of course, we don't know how to produce this function. Yes, but there is a function. So this is just an existence result. Okay. In the easiest case, we can make x to be a singleton, just a point. So there are entire functions for which just one point is a component of the escaping set. But, okay, so how do we go about constructing this? Again, you may have seen me talking about this in connection to wandering domains. So we will construct a function. This is very similar to the first construction. So if you follow the first part, you're safe. So what we will have is this infinite collection of house strips that they accumulate to this half line that joins a point zeta to infinity. So this line, I call it K, of course it's not compact anymore, but it plays the role of the K before. So K, again, is an intersection of all these half strips. Yeah. So we have this point zeta here. In order to find to make a counterexample to Eremenko's conjecture, you only, okay, so again, as before, the boundaries of K, we will map them to basins of attraction. This time we can map the whole boundary of K, Kn, to the basin of attraction because we use more powerful result, namely Merkelian theorem. So each of the boundaries of the Kn will be mapped to the basin of attraction. Okay, as before. So this point here will be escaping, right? We want to make this point escaping. So then you wonder, okay, what if I make this point escaping? What could the component of the escaping set containing this point look like, and how do I make it bounded? Well, it will not be able to go outside this half line because here you have all these half rectangles that accumulate this. So the only way that this component could be unbounded would be if it's like this line, okay? Because there is no other way for this component to grow. How do we make sure that it's not just this line at the end? Well, we make sure that there is one point here that has an oscillating orbit. If we put one point that has an oscillating orbit, then there will be a bounded component of the escaping set containing this point. That we don't know where it finished, but it will be some subset of this part of the line here. Okay, as I said, this is enough to make a counterexample to Eremenko's conjecture. Now, if you want to obtain a function that has a singleton component of the escaping set, so say you're more demanding and you just want component of the escaping set that is just a point, then what you need to do is pick a sequence of points here in the bungee set, converting to this point, so that each of these points is a bungee point, right? So each of these points you make it bungee, then point you make sure it's escaping, then this escaping point is exactly a component of the escaping set. Now, if you get more demanding and you want to have, as I said here, any full continuum such as the Mandelbrot set, then what you can do is, instead of having here a point, you put here the Mandelbrot set and you join it to infinity with a ray and follow the same procedure as before. You would have the Mandelbrot set here and then this ray, and then instead of having rectangles, so to the right they will be rectangles, to the left they need to be replaced, for example, by this equipotential, the version of equipotential curve around the Mandelbrot set, right? But it does not matter. What we care is that close to infinity, these are horizontal lines, so we can measure distances between them, and we're fine. Okay. So now, with my last 10 minutes, I will only discuss the first case where we have a point here escaping, another point here bungee, and the boundaries of these rectangles, they will be preimages of a basin of attraction. Are there any questions about the setup of what we are set to do? No? Okay. Okay, so what we will do basically is modify this map that is 5 times that. I think everyone is very familiar with 5 times that. So what does it look like? So first of all, let's look at this first. So here, okay, so you have the, imagine you have the map 5z exactly, right? So if you look at this strip S0 that goes from imaginary part 1 to imaginary part 2, the image of this yellow strip is this strip here that goes from 5 to 10. Okay, so the yellow one under 5z, it covers this. Since this has height 5, again, we put 2 strips similar to the ones we had here, a yellow one and a blue one. Then we look at the yellow one. This goes from 6 to 7. So under 5z, this goes to wherever it should go. Right? So yes, 30 and 35. Yes. Okay, so we keep doing this. So we define this collection of strips. The formula is in the previous slide, but basically we have 2 strips, then look at the image of the yellow one, then put 2 strips, then look at the image of the yellow one, etc. Okay. What else do we need? So these are these strips SK and TK. We also have a disk. In this case, we put the disk here. The role of this disk is the same role as the disk before. We want the disk that map inside itself, so that whatever we throw into the disk needs to be contained in a basin of a function. Okay? So we have this disk. Every function, again, we will construct the functions as a sequence of entire functions. In this case, we will use, instead of Runge, we will use Arkelyan's theorem, because we need to approximate on unbounded closed sets rather than compact sets. Okay. So the idea is similar to the one we had before. So what is the structure here? Our sequence of functions. So first of all, there is this principle that it needs to converge to a transcendental entire function. So we will have larger and larger horizontal strips where the function will agree more and more. So these strips will grow and grow, and we are not allowed to change the function there anymore. So at every step, we have the freedom to define the function in this new strip, and then eventually put everything inside the block and say, okay, this I don't change anymore, then I change it there. And then in the next step, I increase the place that I don't change and then change the next part. We keep doing like this. Now, the reason we put 2 different colors, besides being 2 nice colors, in these strips is that the yellow ones will always be close to 5z. So on the yellow strips, the map is very close to 5z. We don't change them. What you change is the blue strips. So the blue strips is where the magic happens, if you want. So what we will have is this picture that I put here. This lives into T0. Okay? And the dynamics will be similar to this. Things will move from T0 down to S, so from T0 to S0. Then in the next step, it will go up to T1. Then T1 maps to S0, S1, T2, then go down. So basically, you keep going up n times by going through the yellow strips. At the last step, you jump to a blue strip, and then the blue strip brings you down to S0 with some nice wave. that we have the properties that we want. This is where we have the control. After this, the map that you had brings you up again to the n+1 strip, and then you map down again. Yes? Only looks confused.
No. So they will escape, the escaping points will escape to the left,
Yes, so
right? Or
the idea is that all the things that you map outside some interval here, if you map it to here, for example, then 5z keeps bringing you to the left. And then when you map down, you keep going again to the left. If you want to make a boundary point, then you need to keep mapping this point to some bounded part of this strip, right? So all the points will do this. In terms of the imaginary part, they keep oscillating, right? But in terms of the real part, if the point is to be escaping, it needs to also keep escaping in terms of the real part. If it goes to a bounded part, then it will be a boundary point. If it keeps returning to this compact set, which is some bounded interval in terms of the real part, and inside the zero. Okay, so this is the recipe. I don't know how much I want to say about this, but basically, we need to have this thing where things come back to the strip S0, right? So for every function in our sequence, we can define the preimages of T1, T2, T3, blah, 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 inside S0. So this is this set that we call VJ. So this is a collection of topological strips inside S0 with a property that if you throw something in there, then under 5Z, it keeps moving to the place that you want to go, right? So again, we have this property that the image of the boundary of Kj after a suitable iterate maps to the disk D. So the boundaries of Kj will be preimages of basins of attraction. And the map that we had before, the map will be injective, so univalent on these sets we're defining. And
Is this a requirement for the construction to work, injectivity, or is an extra property that you want?
Yeah, I think we really need to use it. I think the fact that, yeah, this is okay. So for example, with Basso, we do things where they are not injective, and then we have other types of problems.
I thought it was maybe you wanted to make sure you only had one premise at some point, but maybe I don't know if.
So this is because also we track all these. So basically, at each place, we have something that looks like this. If you start having critical points, this becomes complicated. So you need to be able to track this structure within your set, if that makes sense, right? So you have, yeah, I think that's why it needs to be univalent, because at every step you need to be able to say what is Fj of the boundary of Kj, and so have some control on what is the shape of this set somehow, I think. Okay, so, and then as I said, like, if you want to make the point zeta at the end of this ray escaping, then you need to make sure that you have something like this, smaller than -j, every time that you return to the strip S0. Okay, I think I'll finish here.
Very much.
So.
Yeah.
I could not follow. How do we ensure that the degrees of the polynomials has increased to infinity? Then only the limit will be.
I mean, so the limit function, we know that it's not a polynomial because it does not behave like a polynomial near infinity. 1 second. So, for example, when here, so the resulting function will have this sort of behavior. So there will be points that are arbitrarily to the right, arbitrarily far to the right, that get mapped to this basin of attraction. So this is not something that a polynomial could do. There are many other things that the polynomial couldn't do, but maybe this is the easiest one to see. Yeah.
So I understand that this is related to Letitia's question. So this wandering domain, every component of this compact set in this construction will be a wandering domain, a univariate wandering domain, right? Because
Yes.
of your requirement of translation by one unit of
Yeah, yeah.
objectivity.
Yes. So,
And here, in this construction, sorry, let me.
so here, instead of having a wandering, so here we have this K is array. You could have also a strip. You have the strip, no, like this intersection, they do not degenerate to a array, just to a strip. This strip would be,
right?
it would be, yes.
Whatever.
Would be a univariate wandering domain.
Again, this will be a univariate one.
Yes. I will be talking about wandering domains.
Next week.
Yes. In particular, hopefully, about non-univariate wandering domains.
No questions?
Yeah, I struggle to imagine, so this point is straight to the left,
Yes.
right? But then you know that when you take the closure, it's unbounded, whichever connected components,
Sorry.
right? You take, so the connected components of the closure of the state instead are unbounded.
Yes.
So how the component
I can draw. So we have the half script. Then we have some color. We have this ray. And what is happening is that, so this point is escaping. And then there are, so these white points, they go to the basin of attraction. Right? But in between these parameters of the basin of attraction, there are unbounded components of the fast escaping set that accumulate to this escaping point. So this is picture similar to what I drew before. This component of the escaping set needs to be accumulated by other unbounded components of the escaping set, so that the escaping set union infinity is connected.
you need to construct, you know, it needs to exist because of the
Yes.
terms.
If there is no contradiction in mathematics, we should have it. Yes.
Okay, then.